Hey guys, this is Mr. Perry, your chemistry teacher. I am going to show you how to go through this molecular structure lab. It's 03.05, I believe. Doesn't show it right here, but yeah, I think it's 03.05. I did a live lesson for this, and then I totally forgot to hit record, so I'm just recording it myself. I'm going to help you out with this thing, so you can read through all this stuff, and you should before you start this lab. But I've already downloaded the lab report, and in fact, I filled a little bit of it out already. It also wants you to use the polyatomic ion list, VSEPR geometry chart, and electronegativity chart to complete the lab activity. You don't need to use the polyatomic ion list. I didn't find that it was necessary, so you can ignore that. But the VSEPR geometry chart and the electronegativity chart, that is going to be pretty helpful. Okay, so let's look at the lab. Sorry if you hear my cat stomping around in the back. He's in his litter box right now. I think I'll just hit pause and then we'll resume the video once he's done stomping around. Okay, so he is finished, so let's keep going. All right, so first off, the title. I'm not too picky about the title. I put Polarity of Substances Lab because if you look at the instructions, it says you'll investigate why certain substances such as oil and vinegar don't mix. To do so, you will combine various compounds, compare their solubility, and determine their polarity. So at the end of the day, we're trying to figure out the polarity of these substances. So I just put Polarity of Substances Lab. Objectives, I kind of just said that. Determine the polarity of various substances by mixing them with substances of known polarity. All right, that's the objective. And you can sort of come up with your own objective, but that is the basic one. The hypothesis, I'm not going to write that one, but it says create a hypothesis that predicts the polarity of iodine solution, vinegar, vegetable oil, salt, water, and rubbing alcohol. Literally, just type in what you think will be polar and what you think be non-polar. You can just completely guess. Like, I predict that, vinegar, vegetable oil, and rubbing alcohol will be nonpolar, and the other stuff will be polar. Anything like that. That one's pretty easy, so I'm going to skip over that. You can just type that in yourself. Shows you the materials. Obviously, I don't know where they expect you to get iodine solution. Actually, you can get them at the store. This is like, I think you can get it in the first aid aisle, but that's okay. We're going to do it anyway, so I'll show you that stuff in a second. Safety, I'm not too worried about safety for this lab. We're using very basic household items, but it's always good practice. Okay, variables. Here's what you're going to write down for variables, all right? So the controlled variables, the independent variable, and the dependent variable. Let's start with the controlled variables, things that are going to stay the same in this lab. And if you look at the materials, well, I think that's the control right there, are the materials being used. And when I say materials being used, what I mean is the glassware you're using, or in my case, the plasticware, measuring devices, ingredient brands, right? Like I'm not going to use a different brand of iodine solution for like in the second cup than the first kind of thing. So that's what I mean. So just put that for your control variables. For your independent variables, okay, what you're going to do is you want to look at these the summary of steps, and it looks like when you read through these steps, you're going to see that each time you're basically changing. The thing that you're changing is the step that you're mixing in your solution. So like, for instance, in this part, it says you're using deionized water and iodine solution. I'm going to actually have to go over this in a second because this is wrong. But the point is, the independent variable are the substances being mixed, if you want to just put it simply put. And the dependent variable would be whether or not those substances mix, right? Because whether or not they mix depends on the substances being used. So that's your independent and that's your dependent. You can make it sound a bit more sciencey if you want to. You can articulate it a little bit better, but that's okay. I'm just trying to get through that stuff quickly. Okay, one thing that's very, very important. Summary number 2. It's wrong. I can't believe that, but it is incorrect. It says, look here, it says add about 2 tablespoons of rubbing alcohol to a cup and 2 tablespoons of iodine solution to another. But you're not supposed to be using alcohol. You're supposed to be using vinegar here. So this should actually be vinegar, all right? This should be vinegar. Okay, so fix that. Okay, that should be vinegar. In fact, if you look at these tables, look at what it says, vinegar and water. Not rubbing alcohol and water, vinegar and water. We use rubbing alcohol later, so just keep that in mind, all right? But anyway, they give you the steps. You don't have to list any steps here. They give it to you here. We're going to start with step 1, I think. Okay, so step 1 says, using the steps for predicting the polarity of compounds, determine the polarity of water. Place your answers in table 1. So let's do that. If you remember, the first step is we need to figure out well, I don't know if it's the first step, but basically what we need to do is we need to figure out the Lewis structure for water. Okay, so we're going to do that, and then we'll go from there. All right, so we know that water is composed of 2 hydrogens and 1 oxygen atom, right? 2 hydrogen atoms, 1 oxygen atom, H2O. So what I'm going to do is, the first thing I'm going to do is I'm going to go to the periodic table, okay? And I am going to find hydrogen. Now, hydrogen is in column 1, which means, okay, any element in column 1 has 1 valence electron, all right? 1 valence electron. So what I'm going to do here, I'm going to go ahead and draw the valence structure for hydrogen. So here's H for hydrogen, and we know it has 1 valence electron, so we're just going to put a little dot there, okay? We're just going to put a little dot there. All right, now we're going to do the same thing for oxygen. Okay, let's find oxygen. You can actually see it right here in the right over here. Now it's in column 16. If you look here, that means it has 1, 2, 3, 4, 5, 6. All right, anything in this column has 6 valence electrons. So I'm going to draw oxygen, and I'm going to write that it has 6 valence electrons. So it's going to be 1, 2, 3, 4, 5, 6. All right, it's got 6 valence electrons. All right, now that I know that, okay, we're going to figure out what this would look like if it were water, right? Because water is composed of 2 hydrogens and 1 oxygen. So let's think about this for a second. I'm gonna draw this right in the middle here, okay? So we have our oxygen, which again has, looks like that, more or less. Now, one thing to note is that oxygen, it has these lone pairs, which are stable, right? We don't need to do anything with them, but it has these guys right here, these single electrons, right? These single electrons. And those single electrons don't want to be like that. They also want to be paired up, okay? Because remember, oxygen wants 8 electrons in total. Right now it only has 6. So what this is telling us is that if this were to form a covalent bond, and since hydrogen is a nonmetal, it will, it's going to want to form a bond with hydrogen. Nope, let's make this black. So I'm going to draw hydrogen down here with its 1 valence electron. And remember, what's going to happen is that these guys are going to share their electrons, and they're going to form a pair. And the same thing is going to happen with our second hydrogen, right? Because remember, H2O, right? We have 2 hydrogens. Hydrogen has its, lone, or its single electron, its unpaired electron. So these guys are also going to form a bond. And remember, how do we draw that? How do we draw a bond between, how do we draw a bond between atoms, a covalent bond? We use a line, right? We draw a line. So this is going to be our line between this hydrogen and this oxygen, and we'll draw one down here too. All right, that doesn't look very pretty, does it? But that's okay. You get the gist, right? There. Okay, so that's what water looks like. All right, that is water's molecular structure. It's Lewis structure. Sorry, that's its Lewis structure. All right, so great. So let's look at our table. In our table, it wants us to put the Lewis structure, which we've just drawn, and I'm just gonna make this easy. Let's just Google Lewis structure for water. Right? We've already figured it out, so it's not like we're cheating here. We already know. We've already done the work to figure out what it looks like. So let's just use this image, and we'll paste it right here. Ooh, that doesn't look very good, does it? Let's try pasting it like that. Haha. We'll make it tiny. There we go. Difference in electronegativity of each bond. Okay, so the bonds between oxygen and hydrogen. So let's go to our electronegativity chart, and let's find hydrogen and oxygen. So hydrogen's electronegativity is 2.20, oxygen's is 3.44. The difference between that, so let's do 3.44 minus 2.2. I'm doing it on a calculator. You get 1.24. So the difference is 1.24. All right, 1.24. All right, the Vesper sketch. Okay, so if you look here, here's our little Vesper chart. All right, you should have looked at this before. They should have gone over Vesper theory already. So what we're going to do here is we'll notice that it has a little code here. It says A is the central atom, X is the atom bonded to the central atom, and E is a lone pair on our central atom. So, all right, well, let's think about oxygen here. Let's think about what we've drawn here. So, A is our central atom. So that's oxygen, right? Oxygen is our central atom. Oxygen has 2 bonds, right? It has 2 bonds here and here. And then it also has 2 lone pairs. So we're going to keep that in mind. We're going to look for one of these things that has basically 2 X's and 2 E's, essentially, right? So let's see here. Total domains. So domains, if you see here, it says domain is the sum of bonded atoms and lone pairs. So remember, right? How many bonded atoms and lone pairs do we have? We have these 2 bonds, so that's 2 bonds. And then we have these 2 lone pairs. So 1, 2, 3, 4. So it has 4 domains. So let's look down here over here. So we have 4 domains. So it could be any of these 4 guys right here. Okay, so we know we have a central atom. We know we have 2 bonds. Okay, so it should be X2. Which one of these? So this one's X2, right? And we also know that there are 2 lone pairs. So it's going to be this guy, right? AX2E2. You can put the picture in if you want, but actually, honestly, if you want to, you can just write AX2 if you want. AX2E2, I think it was. You can just write that. That's fine. Right? AX2E2. That's totally fine. You can just write that. Polar, nonpolar, or ionic. All right, so remember, to figure out if something's polar, it has to meet 2 criterion. All right, it has to meet 2 criterion. 1, it has to have a pretty high electronegativity, and it also has to be asymmetric, okay, asymmetric. Now, the electronegativity difference is 1.24, so that's pretty electronegative, so that meets the first criterion. Now we have to look at this Lewis structure and ask ourselves, okay, is this polar, or is this asymmetric? Now, vertically, it is symmetrical, right? But horizontally, it is asymmetric. So it does meet both criterion. Therefore, this must be polar. All right, it is polar. Vector molecule shape, well, you can just look at your chart here. The molecule shape is bent. And the molecular structure, we'll just say it's electron geometry. I think that's what they're asking for, is tetrahedral. So we'll put tetrahedral. Tetrahedral. Because the molecular structure, I mean, we put that. That's basically the Lewis structure. So let's make this font a little bit tinier so it'll fit. Never mind. Whatever. It's fine. Tetrahedral. We know what we're talking about. Okay, great. So that's table 1. All right, so we've done step 1. I know that took a while, but there's step 1 done. Okay, this is where it gets kind of ridiculous. Now you have to start mixing a bunch of things together to determine their polarity. So let's work on that. Okay, so step 2 says put about 2 tablespoons of deionized water into each of 2 labeled test tubes or clear cups. Okay, add 2 tablespoons of vinegar to 1 cup and 2 tablespoons of iodine solution to the other. Mix the contents with a stirring stick. In table 2, indicate whether the solutes, vinegar and iodine, are soluble in the solvent, water. Then conclude whether the compound is polar, nonpolar, or ionic. Hint, like substances dissolve like substances, and polar solvents dissolve ionic compounds. Okay, so that's a lot of information. Let's break that down here. Let's just look at this table. So it gives us that the solute is vinegar and the solvent is water. So first off, it says, is the solvent polar, nonpolar, ionic? Well, we already know that water is polar, right? We just figured that out. That's what we did in step 1. We know that it's polar. So we're just going to write polar right there. Now, I'm going to put my camera on here, okay, so you can see me. All right, let's see here. So I have this little cup here, all right? I don't know if you can read it because I think this is doing like a mirrored thing, but this is water and vinegar, all right? This is going to be our water and vinegar cup. It's not a test tube, and I'm not using a stirring stick. I'm not even going to use 2 tablespoons. I'm just going to mix them together and show you what's going to happen. So I got water. It's not necessarily deionized, but it is distilled. So we're going to put some water in here. Okay, there's our water. All right, now we're going to add some vinegar. We're going to add vinegar to this. All right, shake it around a little. And if you look here, it's kind of hard for you to see, but it does mix perfectly, right? There is no layer. There's no layer of water and layer of vinegar or anything. It just mixes perfectly. So it is soluble, okay? This is soluble. The vinegar dissolved into the water. All right, so let's go back to our table. Was it soluble? It was, so we're just going to write soluble. Is the solute polar, nonpolar, or ionic? Well, remember, okay, like substances dissolve like substances. So if water is polar and vinegar dissolved into it, that means vinegar must be polar as well. If it didn't dissolve, then that would make it non-polar, all right? Okay, so iodine is the next one. So first off, I'm just going to tell you that an iodine solution is made up of potassium iodide, which is ionic. I don't know how they expect you to just know that, so I'm just going to tell you right there. This is an ionic solute, okay? But anyway, we know that water's polar, and we can actually kind of guess that this will probably be soluble because ionic substances are polar, and polar, dissolves polar, but let's just do it. All right, so here's my H2O and iodine cup. Put some more water in there. I'm running out of water. All right, put a little bit of water in there. Here is my iodine solution. You can get these at like the first aid aisle at like a Publix or something. I'm not gonna put too much in here, but I'm just gonna put like a couple drops. Okay, I'm gonna put a couple drops here, and I'm gonna mix this around. And if you'll notice here, actually I'll just stir this with a cup or with a spoon. It takes a while, but eventually it does dissolve, right? It does dissolve eventually. It is totally dispersed. There's no like layer of iodine and layer of water. Ooh, my face looks really weird with the refraction there. But anyway, so this does dissolve, right? This does dissolve. It is soluble. So we are going to write. Sorry if my voice gets like weaker when I move away from the mic, but we are going to put that this is a soluble mixture. Okay, it is a solution. It forms a solution. I can't type for the life of me. Good Lord. Okay, so that's soluble. All right, let's go through rubbing alcohol and vegetable oil now. Get the camera back. Rubbing alcohol. So here's my vegetable oil, right? Here's my veggie oil. Let me just clean up a little here. Okay, so I got my vegetable oil. Just gonna put a little bit in here, just a little bit, and maybe a little bit more. There we go. Now, first off, here's the thing. You know that oil and water don't mix, right? That's just a time-old. That's age-old knowledge. So think about this: if vegetable oil, if oil and water don't mix, what must oil be? Non-polar or polar? It doesn't mix with water, okay? And if it doesn't mix with water, it must be non-polar. So right off the bat, we can just write that in there. We know that because oil does not mix with water, it must be a non-polar substance, okay? So anyway, sorry. Rubbing alcohol. So what we're going to do is we're going to figure out if rubbing alcohol is polar or non-polar by mixing it with, here's my rubbing alcohol. All right, we're going to mix it with vegetable oil. All right, so I'm going to add a little bit. And let's just wait for a second. And you should see that, aside from the bubbles, you should see that the oil is on the bottom layer and the alcohol is on the top layer. They don't seem to be mixing, okay? I mean, I could stir them up and they can mix, but eventually they'll just settle back into these two layers. So since there's two layers here, there's two obvious layers, like here's the alcohol, here's the oil and here's the alcohol. We can pretty much say that they do not mix. They are insoluble. That's the fancy science word for it. They're insoluble. So let's type that in here. Come on, just... Why? There we go. Oh my goodness. There we go. Insoluble. All right, and since it's insoluble, right? If this is nonpolar... Now, if rubbing alcohol were also nonpolar, these would mix, right? Because again, like substances dissolve like substances. But because it did not mix, that means alcohol must be polar, okay? It must be polar. All right, now let's try salt. So here's the thing. We know that salt is made of sodium chloride, which is a metal and a nonmetal. So you should know that that's ionic, right? Salt is NaCl, right? Sodium chloride. If you look at the periodic table, sodium is here. Chlorine is here, right? Metal and nonmetal. So that means this must be ionic. And we already know that vegetable oil is nonpolar. Now remember, think about this. An ionic substance is composed of two ions, a positive ion and a negative ion. And since that's the case, this is probably going to be insoluble because ionic substances are by definition very polar, right? They have a positive end and a negative end. That's what polarity is. It's something with a positive end and a negative end. So I'm going to assume that salt is insoluble, but we will do it anyway. I'll show you on screen. Okay, here's my vegetable oil. Here's a thing of salt. I dumped it in there. And I will start stirring this. Okay, I'm stirring. And I know it's kind of hard for you to see on the screen, but if you'll notice, if you see here, the salt is just falling to the bottom. You see this white layer right here? That's the salt. It is not dissolving at all. Like right in water, if you stirred this in, it would dissolve. Here, it's just falling to the bottom. So this is not dissolving. In fact, you can see some of the flakes in there still. So it did not dissolve. It is insoluble, which, I mean, we could have guessed that. But now we know. Okay, water and rubbing alcohol. All right, well, do we really even need to mix this? Because we know that water is polar. We know from earlier that we found out that rubbing alcohol is polar. So if these are both polar, right? Remember, like dissolves like. So if these are the same thing, will it dissolve? And the answer is yes. So this should be soluble. I'm just going to type it in. Again, I'll show you it. I will show you it. Sorry, it's getting cluttered over with all these things. All these materials. All right, anyway, so alcohol and water. Got my alcohol. Here's my alcohol. Got my water. And if you look, they mix perfectly, right? They do mix. So this is going to be soluble. And I mean, again, we could have guessed that, but now we know. Vinegar and rubbing alcohol. Again, let's see. We know that rubbing alcohol, we've already figured out that it is, it's the solvent here, so it's polar. We know that vinegar is also polar. I think I mixed those two up in this one, but it doesn't matter because they were both polar. So vegetable oil, yeah, okay. So yeah, vinegar, we also know vinegar is polar. And again, we know that because we figured that out in the first table. So if these are both polar, that means they should be soluble because, again, like substances dissolve like substances. But we'll check. All right. All right, got some more alcohol. Here's my vinegar. Might have had too much vinegar, but that's okay. And if you look here, hey, they mix perfectly. They mix pretty perfectly. So this is soluble, as we predicted. I mean, that's kind of what science is about, right? It's using your knowledge to be able to determine, like, theorize what's going to happen. And we did that, right? We determined that vinegar and rubbing alcohol would mix, and it did. All right, now let's do iodine and vinegar. Again, we figured out that iodine is... Oh, I'm sorry, so vinegar is the solvent. So vinegar is polar. And we know that iodine is ionic, which is basically, that means it's polar, okay? Any ionic substance is by definition polar because it's composed of a positive ion and a negative ion, right? It's always going to be polar if it's ionic. So this should be soluble, right? Let's guess. We're going to make a guess here that it's going to be soluble. Sorry. All right, but let's try this here. So again, it's vinegar and iodine. So here's vinegar and iodine. All right, there's vinegar. Gonna put some iodine in there. Don't need to use a lot because iodine is pretty dark. But yeah, if you see here as we mix it, look at that. It mixes perfectly, right? No layers or anything. It is soluble. Just like we predicted, it's soluble. And then lastly, vegetable oil and vinegar. All right, vegetable oil and vinegar. So again, we know that vinegar, our solvent, is polar. And vegetable oil, we figured out, well, we already know that oil is nonpolar, right? We figured that out over here, right? Vegetable oil is nonpolar. So I'm going to put nonpolar. So will these things mix, right? Will nonpolar and polar substances mix? Remember, like dissolves like. So these are not alike, so they will not dissolve. So it's going to be insoluble. But again, I will show you. So here's my vinegar. Put some more in there. Right, here's my vinegar. Here's my vegetable oil. Just gonna put the cap on. Do not want oil to get out because it is very hard to clean. All right, and I'm gonna try and zoom in closely. You see here, I know my camera's not the best and the light's not helping, but you see here how we can see that the oil is on the top and the vinegar is on the bottom. You can see that distinct layer right there. They are insoluble, right? They are insoluble. Okay, and you probably have water and oil at your house, so you can try that on your own. Okay, I think that for conclusions, I think you can figure that out on your own. That's pretty easy. I will say for the post-lab reflections right here where it says, were any of your substances difficult to identify as polar or nonpolar ionic? I mean, I'm the one that identified them all for you. So what I would do for you is I would put no. But I will say one thing that I would have liked is since, you know, alcohol and water and also vinegar, they all kind of had the same color. I think in the future, it would be prudent to dye the clear substances. I should say the colorless clear substances with food coloring. That way in the future we can kind of see easily how if they mix or not. So that might be an answer for that one. But again, you can figure out the conclusion. You've got the data here. We've done all this. We've done all the hard stuff. All right, well, look, I really hope that helped. I know that I'm not amazing at making these videos. I know there's probably a lot of errors here and there, but I hope this did help. And I hope you guys have a great day. And if you have any questions, feel free to text me. Goodbye.